So hello, everybody. First, the introduction, and thanks to the organizers for giving me the chance to present my work here today, which I've conducted in the University of Geneva in the group of Aurelien Roux. I'm now actually in the group of Xavier Trapat in Barcelona, so I've moved back to Barcelona where I am continuing this project. So today I'm going to talk about nematic 3D tissue protrusions, nematic tissues and what nematic tissues are and what nematic tissues can do. So the first thing I'm going to do is to talk about the word nematic, which I'm sure most of you know about, but for those of you who are not familiar with the word, nematic is a word that was invented to describe liquid crystal phases. So liquid crystals, for those who don't know what liquid crystals are, these are fluids that behave like normal liquids, but present internal order like solids do, like crystal solids do. So this molecular order that liquid crystals present give like amazing properties to these fluids, like these birefringence that you see in the screen. So the fact that you see white and black parts is because these fluids can interact with polarized light, and this gives this characteristic pattern of liquid crystals. Another very important thing of liquid crystals is the fact that they present topological defects. These are the crosses you see in the screen. These topological defects are regions where the order is completely lost, and these are required to merge actually the different domains of different orientations. So one may wonder what happens in 2D. So if you draw a pattern, a nematic pattern in 2D, this is the kind of shapes you are going to get. This, I'm sure, is familiar to most of you. This could be a fingerprint, for example. In a fingerprint, we get these regions as well that are disorganized. So the core of these regions has no order, and around these regions, the order is very well defined. So the orientational order around these configurations is always the same. So these are called topological defects, and in particular, these are +1/2 and -1/2 topological defects, and these are the classical arrangements that we see in 2D nematic liquid crystals. So one could think that these systems could be active. So if we make these units active, you can have a system that has these topological defects, but now these topological defects move because the orientation around these defects gives like a non-symmetric configuration. And then these active units that organize in nematic patterns in these systems make the system move like this. So one of the nice things of topological defects, especially in living systems, is they entail certain mechanical patterns. And this has recently been really important to describe different biological processes. This is work from Aladou. Actually, these are topological defects in epithelial cell monolayers. They spot these defects and they extract the stress patterns of these defects and correlate the position of the defects with extrusion in these cell monolayers. Other defects have been found, for example, in cell monolayers of neurons. And here these defects correlate with difference in cell density. And most recently, work from the group of Kineret Keren with Hydra. This is like an amazing creature, a very simple multicellular organism that has 2 epithelial layers and a mesh of actin that is supercellular and features as well topological defects. And the nice thing is that the position of these topological defects correlates with very important parts of the animal, and as well gives certain topological structure to this organism. So here, as you see, we see these kinds of defects, +1/2, -1/2, but the ones we are seeing as well are these +1. So these are integer topological defects, and these ones are really difficult to spot in vitro. So this was our obsession. Our obsession was to prepare nematic tissues that could feature these integer topological defects. And to do this, we used these muscle cells, which as you see are really anisometric. So they will give rise to nematic phases. They perform mesenchymal migration, meaning that the cell-cell adhesions are really low and they slide one past each other when they are in monolayers. And they are highly contractile, so we picked like very strong cells. So the easiest experiment you can do with these cells is just you take a glass and you plate the cells, and you will see that as the density increases, these cells get a more and more anisotropic shape. And at some point when the density is high enough, they will feature really elongated shapes and will give rise to these nematic patterns that we are talking about. So as these nematic patterns emerge, you will see this is a video of like around 40 hours. And at the very end, we reach this nematic-like state, order and topological defects. So what we do with these monolayers, we can get the orientation from the intensity maps that you see in the screen, and we can localize these topological defects. And we can find like characteristic length scales of this material. Here I zoom in a little bit, so you see clearly these two kinds of topological defects in layers. So what we wanted to do, as I said, is to create these +1 topological defects. So one easy way to do this is by confining the cells in specific geometries. Something that I forgot to mention. So in this unconstrained situation, the cells do not perform collective migration. So they follow the orientational field, but the trajectories are totally, are in the two directions. So the cells are not polarized. There's not a long range polarization of the cells. So they follow the nematic field, but the migrations are in the two directions, let's say, following the nematic field. So what we wanted to do is to confine this system so that we could get rid of these +1/2 topological defects and get a smaller confinement with one single defect in the middle. And to do this, we used Primo. So of course we could use other technologies, but Primo has been really useful to generate really stable patterns. So in my case, I need pattern stable for 2-3 weeks. So Primo has been probably the best tool to do this. Probably all of you know how micropatterning works, but basically you coat a substrate with a repellent polymer and then you burn certain regions, you put the protein of interest, and cells love this protein but hate the polymer, so cells will stay constrained in the region you've patterned. So when the confinement is strong enough, these are the two possibilities you could find in a nematic system. You could find ring defects, aster defects, and infinite spirals in the center. So to make the story short, these are the structures we see. So when we confine this system enough, we see that cells can arrange at low densities almost parallel to the boundary, and they now perform collective migration. So confinement gives the boundary conditions necessary for cells to perform collective migration. And we see this collective rotation that a lot of other people have seen with other cell lines, but here the interesting part is that we have long-range orientational order featuring this spiral-like defect. And when density increases, this is the other island that we see. This is an aster defect, cells arranged perpendicular to the boundary, and we don't see rotation. But an interesting point of these defects is that they are non-motile, so all is being dissipated in one single point. So one of our interests was to see which are the forces that these defects generate. This div that I put in the screen is days in vitro. So you will see that this is important for my project. In this case, asters have been growing in these like well-defined regions for 3 days, but I have systems that evolve for 4 weeks. So you will see this in the slides. So we can characterize orientation and flow, so morphology and the speed in these islands. And this has been really useful to predict forces in these regions. And that's why, for this, we teamed up with the Carsten Kruse group in the University of Geneva. In particular, Carlos Blanc has been the one leading this theoretical study. He basically did something really smart. He took the velocity profiles for spirals of different sizes and the orientational fields for spirals of different sizes and predicted certain material properties of this system and extracted the main active components of these systems, which in this case are traction forces and anisotropic and isotropic stresses inside the cell monolayers. And with this, he got like a zoo of active configurations that could take place in our case. But to make the story short, what he predicted for our asters are compressive forces. So he predicts that asters with these material properties that feature rotation in spirals should present compressive stresses. And this is actually something we see. So from 3 days in vitro after the aster transition, we see accumulation of cells in the center. So we see changes in density, and as you will see in a second, we see changes in pressure inside these confined monolayers as well. So something I've not told you is that these cells, these are myoblasts, so these are muscle cells, they want to differentiate. to make muscle fibers. So the first step is cell fusion. So for this cell fusion, cells need to be aligned. That's why we get nematic patterns, because these cells like to be aligned with each other. And after like 3-4 days under certain conditions, these cells will start differentiating and making myotubes, which are the yellow things, the yellow tubes you see in the screen. Actually, here we stained myosin heavy chain, which is the protein that these cells express once they have fused and they are differentiating into muscle fibers. So when we use these cells in our islands and we stain the same protein, we see basically, this is probably the most beautiful example, but if we do an average, you see that the expression of this protein is happening at the very center of these islands, where in principle the pressure is the highest. So this is how the force is dissipated in these islands. Another way to do, so another possibility is that these cells do not differentiate. So we've transformed this cell line to an old cell line. We call it old because basically we've passed this cell line for a lot of time. So until it gets old and the differentiation is not, it's hampered. So it's not easy for the cells to differentiate, and they basically proliferate. And when we do the same experiment with this cell line, what we see is we see growth. So we see growth at the very center of the island and up to millimeters. So at the very end of the presentation, I will show you the longest protrusion we've grown, but this happens like in the range of weeks. So these protrusions that I'm showing here are probably from protrusions that are 12 days old. I mean, I forgot to put it here, but these are 12 days. So that's why we need stable patterns. So you see that at the bottom left part of the screen, you see cells escaping from some of these patterns, but others at the top are really, really sharp still. So this is after 9 days at 37 degrees and everything. So this is quite remarkable. And actually we can have these patterns for longer, as I was saying, up to 12 days, we start seeing like really, really long protrusions. They tilt at some points and we see sharp edges. Normally after 2-3 weeks, we still see sharp edges. And I think this is thanks to primo patterning. This allows us to grow like really big protrusions that feature weird shapes at some point, like these curly shapes due to the forces that these cells are exerting in these configurations. And actually we still see order and defects in 3D. So we consider these 3D tissues as nematic tissues. So these are 3D nematic tissue protrusions with long range nematic order and topological defects. And this order and these defects are the ones that are reshaping the protrusions in time and in space, the dynamics and the morphology of these structures. This is another example. So one of the things we wanted to do is to reveal, to expose these force patterns that are emerging in these configurations. And the way we started is looking at the nuclei, so using nuclei as pressure probes. So we observed that the nuclei volume was not homogeneous in these islands. So what we did is we segmented a lot of these islands, the bases, because for imaging problems, we cannot image the whole structure, but we can image properly the base. So we did this for a lot of different islands. We segmented the nuclei, we extracted their positions and their volumes. And what we can get after easily is like the radial profiles for density and volume. And what we saw is what theory was predicting, which is accumulation of cells in the center of the islands and lower volume at the center of the islands, which is consistent with this increasing stress at the center of this island. Sorry, my slides stopped. No, okay. And from this nuclear volume, we can easily get compressive stress by assuming certain elastic properties of the nuclei and comparing the nuclei with the peripheral nuclei, which are not compressed. So what Carlos did is he got these density profiles and fit the theory and got these forces for our islands and predicted as well the compressive stress, which is fitting pretty well with our experimental data of the nuclei. What Carlos was a little bit annoyed of is with this cell number density profile, which looks a little bit weird. And we assumed this was because of 3D artifacts or 3D conditions that we were not considering in the model. So we basically made younger protrusions, and this is what we get now. The cell density fits well with the theory, as well as the compressive stress that we get from the nuclear volume. So after, what we wanted to do is to measure these forces. That's why we engineered these force probes. So the way to do this, I mean, we took advantage of the fact that we have center symmetric structures, and that they can close really big gaps. So as you see, we will get an aster now that is compressing the center, even if the adhesion is really, really low. So we have a system where traction forces are not so important, and where internal bulk stresses are predominant in our case. So what we did is we put elastic pillars in the center, hydrogel pillars, and we basically looked at their deformations to get the forces. And this is quite straightforward. So from the decreasing area or volume of these pillars, we can get directly the forces that are acting on these structures. So to get a 3D, well, this is the segmentation. So we segment the base of the pillar, basically. And we can get the reduction of pillar section area, and from this we can get the stress that is acting on these pillars in time. So to do it in 3D, we made these pillars fluorescent, basically, and the way to do this is really easy. So you get a glass plate. You can functionalize it with different things, but the easiest version is with a glass plate. You can polymerize hydrogel pillars with Primo. You can functionalize after with PEG, and then you can burn certain patterns with Primo again, and you put your protein of interest, and then you will plate the cells. And this is what you would get. So this, after 3 days, is like a 3D rendering of the pillar and the nuclei around the pillar. And you clearly see that this pillar is compressed. And we see this compression in 3D now. So we can see it as well in 4D. So you can have the 3D rendering of the pillar in time. And we can get the constriction forces in time as well. So that's a tool we've used. So this is really nice to get the maximum pressure that is acting at the center of our protrusions. But what we are not getting, so we get the maximum pressure, but what we are losing is the gradient. So to prove that our protrusions have a pressure gradient inside, what we did is to place the pillar off center. And if the gradient really exists, if we have a force gradient inside our mounts, the pillar should bend in principle. So this is what we observe. The pillar has a strong bending towards the center, where it pops out basically where the pressure is maximum, but it's in the center of the gradient of pressure. So this is quite nice. And this would be the summary. I think I've been like super fast, but yeah, I'd be happy to answer any question. So these cells feature nematic order, and under some confinement, we can generate center symmetric orientational defects, which we call, which they are actually +1/2 defects, spirals and asters. And these localize mechanical stress. This mechanical stress is used in these monolayers, and as well could be used in biology to generate certain forces in certain regions, which in our case localize tissue differentiation and tissue growth. And as I said in the middle of the presentation, I promised that I would show you the biggest protrusion we've grown, which is this one. This is up to 1 millimeter. You see that is like enormous. This is in part thanks to the stability of the patterns. These are 16-day protrusions, and we are growing bigger things at the moment. But these 3D structures are really rich, and this is one single cell line. So I think we can expect a lot of things from this kind of systems. And with this, I will finish with acknowledgement. So I would like to thank as well Professor Aurelien Roux for the opportunity to start this project in his lab, and Professor Carsten Cruz as well, and Carlos Blanc for the theory input, and funding agencies for money, and you for your attention. Thank you.
Okay, thank you very much, Pau. So please feel free to ask any question you may have in the chat box, and maybe I can ask the first question. So I'm super impressive to see this growth of this huge 3D structure. You mentioned that it's somehow due to contractility. So my first question is kind of obvious. Have you tried to inhibit cellular contractility, like using blebistatin, and did you observe like a collapse of this 3D structure?
So this is a very nice question. Of course, it's the first experiment I did. So first of all, with the 2D, we see changes. So we see that spirals change when we inhibit contractility, but we couldn't manage to alter really the 3D structure of these protrusions. So they are very compact, and it's difficult to image and probably to alter the inner cells with drugs. So this we are working on this.
Okay, thank you. And yeah, maybe another question. So these muscle cells are of course contractile. So do you expect to observe the same behavior with I would say less active cell lines?
So sorry, we'll stop sharing because I think it's better like this. So we've tried with other cell lines and we see similar defects, but of course you need this anisometric shape to get spirals or asters. We've tried with some epithelial cell lines, but we don't get growth. So the growth is really related to this cell line which we've transformed, wanted to differentiate, but now cannot, and can basically only grow, and this is what we get. We are basically generating like a tumor-like tissue in vitro with this cell line. Growth, it's easy to get, it's difficult to get. So we've tried with other cell lines, but this is the only one that feature this kind of structures.
Okay, and so we have a question from Isabelle Tardieu. So she's asking, do you see some death cells along with compression, and could this process be related to physiological situations?
We cannot hear you, Pierre-Olivier.
Ah, sorry. Can you hear me now?
You're back, yeah.
Okay. So the question is, do you see some death cells along with compression, and could this process be related to physiological situations?
So I would say we don't see cell death. So I will show you what we see, these super long protrusions. We've tried to clear the tissue, and what we see inside is quite amazing. So we see huge compression, and nuclei are super deformed. I'll try to find the slide, but they look nice. So they look very deformed, but they don't look like cells are dying. We've not done like proper staining of cell death or anything like this. But you see that nuclei inside. So we get these channels. You don't see the screen. Sorry, you don't see the screen. Can you see my screen now?
Yes.
Yeah.
Okay. So this is what we get. This is a tilted protrusion, and when we clear the tissue and image inside, we see like really deformed nuclei inside the tissue, and we see this kind of like vessels forming inside the protrusions, which is quite amazing. But we don't see cell death. So cells grow and they are happy. They are quite compressed in the center, but we think this is a strategy of the tissue to favor cellular transport. So this is something that we are studying at the moment. But I would say no, we don't see cell death.
Okay, so we have more questions popping up. So we don't have time to take all of them. So again, we will be able to discuss this at the end of this symposium. So but maybe one last question. Did you try to vary the density of fibronectin and look at the integrins?
Yes. So this is an experiment we've done. So we've used Primo for this as well. Let's see if I can show you this. So we can control density by just doing this dynamical patterning. So this is what we've done, and the cells don't look really nice at the beginning because they've been like with low volume of medium for a long time. So this is after 3 days, and after 3 days, we basically free space by repatterning. And what we see is that cells start spreading perpendicular to the boundary. So like an aster, what we would see basically in high density. And when they touch the new interface, they arrange parallel to the interface. So basically we see a transition from an aster defect, as you see in the center, to a more planar configuration at the boundary. So this has been like probably the key to reveal this influence of the density. And even we see rotation at the end of the video. So yes, we can change these conformations with changing the pattern in time.
Okay, thank you, very interesting. I guess we can keep on discussing these aspects at the end of this symposium. So yeah, thanks again, Pau.